Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit. And today we're going to be talking about finite and infinite series in this scenario. Let's get started with a little review of sequences. Right, so sequences are just a listing of numbers, right? So maybe we have a finite list of numbers, right? A0, A1, A2 up to AN. Maybe this pattern continues forever, like an infinite sequence of numbers, A0, A1, A2, dot, 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 and that could go on forever there. Little bit of note, I like starting my sequences with a 0 as the first term. Some people don't, right? This is just numbering stuff. So if you want to X out those and just start with a 1, a 2, they might change some formulas you see in your textbook or things like that, but overall this doesn't really matter, right? The numbering, in a sense, is up to you as the person doing the problem, unless the problem explicitly says it that way. But often they won't say an explicit number, right? You might have things like a arithmetic sequence. This is when there's a common difference between each term. So we have 1 plus 3 is 4, plus 3 is 7, plus 3 is 10, plus 3 is 13. So this is one of the more common types of arithmetic, or types of sequences that we call an arithmetic sequence. We also have a geometric sequence. This time we have a common ratio between each term. For example, we could have 2, 6, then 18, then 54, right? We're multiplying by 3 each time in those cases. So these are some simple examples of sequences that we probably are all comfortable with or have seen before, whether we've heard them called arithmetic or geometric sequences in either case. So what is a series then? So officially speaking, the sum of terms of a sequence is called a series there. All right, so this is then just kind of adding up numbers that come from a list. Now, finite series are always well defined. We have nothing we need to worry about when we have some set number of numbers, right? Even if these are huge numbers, very negative numbers, even if there's a million of these numbers, if you had enough time, you could add up all of the numbers. So finite series are always well defined. We have two examples here from the arithmetic and geometric sequences on the previous slide. 1 plus 4 plus 7 plus 10 plus 13 is 35, right? There are some tricks you can do with this. 1 plus 13 is 14. 4 plus 10 is 14, 7 is 14 divided by 2, so we have kind of 14 plus 14 plus 7, or 5 times 7 is 35. There's some nice patterns for adding up terms in a arithmetic series. We're not going to talk about those too much in this video, but those are some good things to think about as well. And we also have a formula for the geometric series. So we have 2 plus 6 plus 18 plus 54 is 80. We'll talk about more patterns and ways you can come up with stuff for those type of series in the later slides today. Now, when we talk about infinite series, they may not be well defined. We need to be a little bit careful what we mean by kind of an infinite series. We're not going to do too much detail today either, right? I understand that this term well defined is a little bit kind of abstract, and if you really wanted to study these in more detail, you would have more formal definitions. But for now, let's just kind of have a rough idea there. And so if it's well defined, it is called convergent. And otherwise we call it divergent. And so the word convergent is a nice way of intuitively understanding what well-defined means, because that means the kind of series is getting closer to some number in this case. So let's take a look at an example of that. So this is actually a geometric series here, right? 1 plus 1/2 plus 1/4 plus 1/8. We're always multiplying by 2 or dividing by 2. This is convergent. All right, so let's kind of see what we mean by this. You could look at some of the sums. 1 plus 1/2 is 1.5. 1 plus 1/2 plus 1/4 is 1.75. If we add the 1/8, we have 1.875. If we add the 1/16, we have 1.9375. So it's definitely getting bigger because we're adding a number each time, but you might be able to kind of guess now that this is maybe getting closer and closer to 2, right? There's actually a lot of nice things you can do with this series. This is sometimes what's kind of done when you talk about Zeno's paradox and things like that, right? We're getting kind of closer and closer to 2. If we take this a lot of steps further, right, this is where calculators or computers and stuff come in. For example, right, you have all the way up to 1 over 1024. This is 1.99023 blah 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 there, right? So this is very, very close to 2 already at this point. And when you're first learning about series, this is a good way to try to understand what the series converges to, if it converges, things like that. This is not a proof of anything, right? But we're reasonably confident, right? We can look at a lot of numbers, it gets close to 2, we're pretty confident that it's 2. So, right, in fact, it is equal to 2. You can prove that. We're going to talk about a kind of general formula for kind of an infinite series like this in the next couple of slides. But this is kind of what we mean by convergent and when it makes sense. It gets closer and closer to this number, and so kind of if you did this forever, which you can't do, but kind of if you did it kind of longer and longer, you would keep getting closer and closer to 2, and that's what we define to be the infinite series would add up to 2 in that case. Now, let's look at an example of a series that is divergent. So if we look at 1 minus 1 plus 1 minus 1, so always plus 1 minus 1 plus 1 minus 1 forever and ever and ever there. I like this example because this clarifies a little bit what we mean by divergent. So if we look at the first two terms, right, 1 minus 1 is 0, but then plus 1 is 1, minus 1 is 0, right, plus 1 is 1, right? So this is divergent because it always goes back and forth between 0 and 1. Right, so we might have some terms that add up to 0, some terms that add up to 1, and we kind of go back and forth between those. Do we ever get closer to 0, closer to 1? No, right? Forever and ever, this is always alternating between 0 and 1, which means that this sequence is divergent, or this series is divergent in this case. A lot of the times, these things might add up to infinity, or right, they add up to bigger and bigger numbers. We'll see kind of an example of that in a second later. But it doesn't have to. A series can be divergent by alternating between different values. It just means it never gets close to one specific value. It never converges on one specific value as we add more and more terms to the series there. Okay, let's look at the geometric series a little bit, and this is kind of one of the more famous ones in terms of formulas and things like that there as well. So let's look at this formula for a finite geometric series. In fact, if we have a plus ar plus ar squared, right, this is our common ratio. We keep adding more and more terms in this case, all the way up to ar to the nth power. We get this equation a times 1 minus r to the n plus 1 divided by 1 minus r. Now let's look at a proof of this here. So we have a plus ar plus ar squared all the way up to plus ar to the nth power. So we have our kind of finite sequence there. And I'm going to keep kind of talking about this because this is going to come into play on the next couple of slides as a little bit of a spoiler, right? But there's no issue here. We said these things are well defined. This definitely 100% adds up to some number s in this case, right? We can add up this whole sequence. We get some answer s. Of course, we want to find what s is. Hopefully, s is this thing on the right side. We want to show that s is a times 1 minus r to the n plus 1 divided by 1 minus r there. Now, the trick we have in this thing is let's look at multiplying this whole thing times r. So we have a times r, so that is ar here. Then we have ar squared, right? So I'm multiplying this whole thing by r in this case. So we have ar cubed plus all the way up to, and now you're starting to see where we have our maybe r to the n plus 1 power, etc. in this case. And so this whole thing then is equal to r times s in this scenario there. So we multiplied both sides of the equation by r, right? This is legal, especially in this context. And here comes our trick. Now we have our two equations, and we want to subtract our equations from here. Let me do the right side first. We have s minus rs. So if I pull out the s here, we kind of have a 1 minus r in this case. And what about on the left side? Well, notice a lot of these terms are going to cancel. The ar cancels, the ar squared cancels, the ar cubed would be the next term, right? That cancels. Ar to the n would be the term right before this. That cancels there. We actually end up with just a minus a times r to the n plus 1. And now we're pretty much done, because if we rearrange things a little bit, we can pull out the a on the left-hand side. Let me flip them over. So if we're solving for s, right, s is, we have our a out in front. Our numerator is 1 minus r to the n plus 1. That's what we have by pulling out the a on that side. And we are then dividing by 1 minus r in this case. So this gives us exactly the formula that we were looking for, right? This s is our sum, and that is equal to this equation, a times the stuff involving the common ratio r in this scenario. So here we have kind of our formula for a finite geometric series in this case. Let's take a look at what happens for an infinite geometric series as well. Here we have to be a little bit careful. Remember, we talked about this idea of converges, and this is actually very important. We'll see this on the next slide, but let's just take it as a fact. We're not going to prove this today, but an infinite geometric series converges when absolute value of r is less than 1. And then in this case, we have this equation, we have this formula, a plus ar squared plus dot dot dot, going on forever in this case, equals a divided by 1 minus r. Now, this is going to look a lot like what we just did. So let's do this kind of quickly here. So we have a plus ar squared plus dot dot dot. And let's say that this is equal to s. Now, this is a little bit where we need to be careful. This is possible because I'm kind of telling us, or we're taking it as a fact, that this sequence or this series does converge. So this does converge to some value s. And if we know it converges, we can do our same trick again. We can multiply by r, so we have ra plus ar squared plus dot dot dot. This is now equal to r times s in this case. And we do the exact same thing where we subtract. So we subtract our values. what do we get here? This one's a little bit weird because all the things kind of cancel out forever. We're left only with a, right? All of the terms cancel on the left side except a. On the right side again, we have s times 1 minus r in this scenario. And so this gives us exactly our formula. S is equal to a divided by 1 minus r here. So that is our trick. Again, it also works for these infinite geometric series, of course when they converge. So of course when absolute value of r is less than 1. Why am I being so picky about that? Well, this is actually very important, because otherwise let's look at this equation. 1 plus 2 plus 4 plus 8 plus 16. Does this equal negative 1? Well, of course not. But this is a geometric sequence and series. 1 plus 2 plus 4, we're multiplying by 2. So what if we try our exact same trick here, right? And so this is equal to, right, plus dot 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 is equal to s. Now, I want to just kind of make this clear right off the bat, right? Right here, we are doing something illegal. You cannot say that this is equal to some sum because it diverges. This doesn't make sense. We can never kind of do that there. But if we do take this trick, if we kind of assume this is where the funny business happens. If we multiply all of our terms by 2, we have 2 plus 4 plus 8 plus dot dot dot, right? This is equal to 2s in this scenario. And so then what are we going to get then here? We do the same exact thing we did before. We take our two sequences, we subtract them, the 2's cancel, the 4's cancel, the 8's cancel, and we are left with on one side 1. On the other side we have s times 1 minus 2, so we have negative s. And so this tells us that the s is negative 1 there. Of course, again, this is a false statement. You can't keep adding the numbers together and getting bigger and bigger numbers and then all of a sudden tell me that whole thing is equal to negative 1. That, of course, doesn't make any sense in this case. But this is why this convergence is important. All right, so this is why I stress that a bunch, because these formulas and the equations we're using, the trick we're using there, only works when you have a convergent sequence. So a lot of the times when you do problems like this, if you want to have tricks like this where you're kind of assuming the answer makes sense, if you're doing it formally, if you're doing it mathematically, you first need to prove that statement. So you might first prove that this series does converge, and then a lot of other tricks and tools open up to you as far as what you can do to look at the problem and kind of come up with answers from there. Let's look at one final example here, and this one is a slight different trick in this case. So let's first try to understand what's going on with this sequence. So we have 1/2, 1/6, 1/12, 1/20, 1/30. Now if you look at the pattern here a little bit, you can start seeing that our terms are going to be of the form 1 over n times n plus 1. And this is going to be starting with n equals 1. So we have 2 is 1 times 2, 6 is 2 times 3, 12 is 3 times 4, 4 times 5, 5 times 6 for all of our denominators in this case. Now, there's going to be some canceling that should remind us of the previous problem, but the trick here is a little bit different. The trick actually is manipulating our terms in this case. Now, I want you to kind of double check this a little bit, right? But this is an algebra fact that we're going to use in this case. In fact, 1 over n times n plus 1 in the denominator is the same as 1 over n minus 1 over n plus 1 in this case there. Right, so we can look at all of these kind of terms in this scenario and kind of start breaking up each term in this manner there. Right, so just as some kind of examples of this, right, we're going to write this down in a second as well. But for example, right, 1/2 is the same as 1 minus 1/2. If we want to look at, for example, 1/20th there, remember this was 4 times 5. This is 1/4. So that's 5/20 minus 1/5, which is 4/20, right? So this kind of is our pattern in this case there. So now something actually pretty nice happens. So if we look at our whole sequence again, right, so we look at 1/2, we're not going to write out all of the terms here, or not even all of the terms listed above, right, 1/6, 1/12, plus ... in this case, right? This is an infinite sequence. This should go forever. But let's start trying to look for the pattern here. Remember, I just said 1/2 is 1 minus 1/2. 1/6 is 1/2 minus 1/3. Right? 1/12 is 1/3 minus 1/4. And so then this is plus ... in this scenario there. But wait a second. We have 1 minus 1/2 plus 1/2, right? That 1 minus 1/2 from the first term combines with the plus 1/2 from the 1/6, and so those cancel out. We have 1/6 is 1/2 minus 1/3, but then 1/12 is 1/3 minus 1/4. So the 1/3s cancel too. The negative 1/4 will cancel with the 1/4 from the 1/20th. And we can see that this is going to continue. No matter how far you go, you're always going to have the next term canceling out stuff in that case there. So this is where the canceling looks a lot like the previous sequences. And in this case, though, there's just one side. We're just straight up left with 1. And that is what the sum of this infinite series is. We add all of the terms up, and they're just getting closer and closer to 1 in this scenario. So it's a little bit of a kind of canceling. It's a little bit of patterns that we're thinking about. But it's definitely another good example to look at and think about in terms of a different type of trick that might come up for an infinite series. That's it for today's Thursday Tidbit. If you liked this video, please subscribe below, hit the like button to let us know that it was a good video. Check back each week for a new Thursday Tidbit this year. And if you're looking for some more practice, check out ziml.areteam.org. I'll see everybody next week. Goodbye.